continue to the single regression analysis, let's learn about multiple regression analysis. In Korean, it is called 다중회귀 분석 or 중회귀 분석. Distinguishing the multiple regression analysis from the simple regression analysis, you just need to remember the number of independent variables. When there are more than 2 independent variables, you perform a multiple regression analysis. But in both cases, the dependent variable is 1. So when do we need the multiple regression analysis? We used the multiple regression analysis in order to describe how well a set of variables is able to predict a particular outcome. A set of variables means more than one variable. As shown here, you can have x1 and x2 as 2 independent variables. Or you square x1 and then treat it as an additional independent variable. In this case, you count x1 square and x1 separately. We particularly name this approach as polynomial regression analysis. Let's look into the procedure of a multiple regression analysis. Suppose you have several variables to measure. So here are 4 variables. And all of them are measured in continuous scale. Then you assign cause or effect. Let's say you consider the first 3 variables as causes. Based on the assessments on these 4 variables, you can perform a multiple regression analysis. The expected result is like this: an equation or a model. The effect is explained by 3 causations. The size of impact caused by each variable can be different. Therefore, the multiple regression analysis gives you the coefficients. The impact of independent variables are comparable in terms of these coefficients, just in case when these 3 variables were measured in the same scale. But when they are measured in different scale, such as height in centimeter, weight in kilogram data, and age in year, as you already have noticed, the coefficients alpha, beta, and gamma are not referring the relative impact size. Do you remember this data table? In simple regression analysis, we tried to quantify the relationship between bitterness and lightness. We already know that a color is made up of 3 independent attributes, such as hue, brightness, and vividness. Depending on color systems, these 3 attributes are labeled in a different way, but the principal aspects are quite identical. So using a multiple regression analysis, we can take all 3 attributes as independent variables. For lightness, we can take the L column and we can obtain the chroma score from square root of sum of squares of A and B, which means in LAB space, we have in 2-dimensional space, we have A and B, and the vertical axis should be L. So in L and B two-dimensional space, the chroma value is actually the distance from the zero orientation. So when a color has a coordinate of A and B here, then the chroma value is simply the distance between 0, 0 and A, B. So therefore, the chroma value is calculatable by calculating the square root of sum of squares of A and B. So this is, we usually write this with a large C. Okay. Lastly, the hue value. Some tried to measure the hue attribute of a color based on the dominant wavelength. Red is converted to 700 nanometer, green to 550 nanometer, and so on. But if your interest is related with human perception of a color rather than its physical properties or energy aspect, my recommendation is to take A and B from the C lab color space. Particularly when you are dealing with object color, which means when the color is actually the reflected light, the LAB values are the most proper way to, or proper approach or proper parameters to quantify the color properties. If you have a special interest in colorimetry or color perception, my office door is always open for you. So coming back to measuring the hue value, we can take both A and B column because the hue of a color has two independent aspects. The A aspect is related with green-red axis, and the B aspect is related with yellow and blue axis. Therefore, my idea is to take actually 4 independent variables because hue has actually a score of A and B. So lightness and chroma and A and B. Here we are in SPSS, and here we need to create a new variable, which is the chroma value. So let's create a new value based on the A and B scores, compute the variable, and here we create chroma, and then A So let's create a new variable. Compute a variable. Chroma will be the name of this new variable, and this will be in square root of A plus B. So A square plus B square. Okay, let's go back to the data set here. Then let's consider this example. 10 family houses were surveyed about their house size and electricity consumption. It's not difficult to guess a bigger house consumes more electricity. A scatter plot indeed shows a positive correlation between house size and electricity. But look at the chart more carefully. Perhaps the plot would fit better to a curve. The implication is that when the house size reaches to 2,500 square feet, they start to consume even less energy. Why is it so? Well, I never lived in such a big house so far, so actually I have no idea. But in fact, such a strange thing occurred due to this house, house number 10. So a large house, but like an eco house, so let's call this house as a large eco house. So perhaps this research focuses on finding the secret or finding a new trend of a large eco house, which sounds quite interesting. So as you see, in regression analysis, you have to observe outliers. Perhaps there is no such a thing like large eco house or curved trend. Simply the number 10 have special reason. For instance, the people have left the house for a couple of months or something. So you should be very careful, or to find out the outliers before you perform the regression analysis, because the regression model is highly sensitive to outliers. So in such a case, a curved regression model is more expected than a linear regression model. Also, it is predictable that a curved regression model will have a larger R-square value. Because we already assume that the curve will have a form like y equals to ax power of 2, so x squared, plus bx plus constant. Therefore, we can create a new variable by adding a new column. It is called as polynomial regression analysis. This polynomial regression analysis is used to address how well an independent variable is able to predict a dependent variable. If there is a nonlinear relationship, such as a curvature, between the independent variable and the dependent variable. Once you have x and x squared, they are treated as two independent variables. So the multiple regression analysis is suitable because you have more than one independent variable, and the multiple regression analysis is taking these two independent variables and calculates the coefficients for each of them. So now we are in Excel and the data are copied here. And based on these data, I created a scatter plot, and the x-axis indicates the house size and y-axis indicates the electricity consumption, like in the lecture slide. And we select the entire 10 dots, and then we add a trend line. Then instead of the linear, we can click the polynomial line, and we can display the equation as well as the R-squared value here. And the R-squared is 0.98 something, and when it was linear, then it was much smaller than the polynomial case. So here, although we initially we measured only one independent variables. By squaring them, we treated it as additional independent variable. So we have two independent variables like x squared and x, and the coefficients are generated in such a way. And let's try this in SPSS in order to examine more things. Okay, now we are in SPSS, and I copied these two variables, and we can create additional variable by squaring the variable of house size. So compute a variable and squaring house size, and this value is initially was empty. So double clicking here, it's moved here, and we multiply this twice in order to calculate the square value of house size. Okay. So we have two independent variable and one dependent variable. Let's shift to upward. Okay. So based on these two independent variables, let's perform the multiple regression analysis. Regression model, linear, and house size and square house size, and as a dependent variable is electricity consumption. And okay, all right, so here you are, and we actually have obtained this exactly same result as we got in Excel. So the R-square value has been identical like this, and the coefficient for the x square, so squared the value of house size, is here appearing 0.00, but because this table only displays up to the third decimal point, so perhaps we can find out the small numbers if we copy this in Excel and then paste it, and then let's increase the decimal points. Yeah, so it has been not 0 but 000451. So it has been rounded at the 5th place. Therefore, we can assume that based on this table, the equation, the model will be appearing in this way. So, unstandardized coefficient is used as the coefficients of independent variables. So, based on this table, we can write down like y equals to, this is the coefficient of this independent variable, and this is coefficient for this independent variable, and this is the constant. The red. Let's change the red letters to black. Okay. So well, constant is also equal here, right? And let's go back to the result, the output of SPSS, and here the model, this model is statistically significant. In addition, one thing you should be aware is to check the multicollinearity among variables. Multicollinearity is, in Korean, 다중공선성. It refers to the relationship among the independent variables. Multicollinearity exists when the independent variables are highly correlated. The multiple regression analysis does not like multicollinearity, and it certainly do not contribute to a good regression model, which implies that when you found out some independents are highly correlated, although the correlation coefficients has not reached to 0.9, or even they have 0.6 or 7, you should be careful, or you should reconsider whether you better include those two independent variables, or you better remove one of them. So the correlations between the variables in your model are provided in the table labeled correlations if you use SPSS. You can check that your independent variables show at least some relationship with your dependent variable. Say above 0.3 are desirable. In this case, those variables correlate substantially with each other. So ideally, independent variables are supposed to be correlated with the dependent variables, right? And SPSS also performs collinearity diagnostics on your variables as a part of the multiple regression procedure. So either you can check the correlation between independent variables in the correlation matrix, or you can check it out. You can check the collinearity in the collinearity diagnostics. And this collinearity diagnostics can pick up the problem more clearly, because by observing simply the correlation matrix by yourself, it's not yet very clear or evident in the whether you should exclude some of the independent variables or not. The result presented in collinearity diagnostics are presented in the table labeled in the table, and the label of this table is coefficients in SPSS. And in that table, you can check two values, and they are tolerance and VIF. Tolerance is an indicator of how much the variability of the specified independent variable is not explained by the other independent variables in the model, and is calculated using the formula 1 minus r squared for each variable. If this value is very small, so less than 0.1, it indicates that the multiple correlation with other variables is high, suggesting the possibility of a multicollinearity. So tolerance should be larger than 0.1. And the other value is VIF, variance inflation factor. This is the inverse of a tolerance value, so 1 over tolerance. VIF values above 10, so when 1 over 0.1 is actually 10, right? So above 10 would be a concern here, indicating multicollinearity. So tolerance should be larger than 0.1. VIF should be smaller than 10. I think you understand the relationship between these two. However, tolerance and VIF still allow for quite high correlations between independent variables. So you should take them only as a warning sign, and you should check the correlation matrix. If you exceed the recommended values in your own results, you should seriously consider removing one of the highly intercorrelated independent variables from the model. Another thing you need to know is the method. When you use a multiple regression analysis for your own research, you better mention what method you have used in the paper. In fact, there are a number of different types of multiple regression analysis that you can use. Depending on the nature of a question you wish to address, you can choose a more proper one. The three main types of multiple regression analysis, three main method types are here: standard or simultaneous, hierarchical or sequential, and stepwise. I personally like stepwise, and this is quite frequently used. So let's check one by one from standard method. In standard multiple regression, all the independent variables are entered into the equation simultaneously. Each independent variable is evaluated in terms of its predictive power over and above that offered by the other independent variables. This is the most commonly used multiple regression analysis. You would use this approach if you had a set of variables and wanted to know how much variance in a dependent variable they were able to explain as a group or block. This approach would also tell you how unique variance in the dependent variable each of the independent variables explained. In hierarchical regression, the independent variables are entered into the equation in the order specified by the researcher based on theoretical grounds. Variables or sets of variables are entered in steps, with each independent variable being assessed in terms of what it adds to the prediction of the dependent variable after the previous variables have been controlled for. In stepwise regression, the researcher provides SPSS with a list of independent variables and then allows the program to select which variables it will enter and in which order they go into the equation based on a set of statistical criteria. It's important that you understand what is involved, how to choose the appropriate variables, and how to interpret output you receive. So let me show you when we work with the method and the tolerance and VIF using this data sheet. So let's try to calculate an equation using multiple regression analysis, and we take these four as independent variables, and let's consider the sweetness aspect. So analysis, regression analysis, linear model, and its dependent variable, the sweetness is here, and as independent variable, these four are selected. And by clicking here, you can collect the descriptive statistics, and which will result you the correlation matrix. Okay, and here is the method. By default, it is standard or simultaneous. And here in SPSS, in the version I have, this is stepwise. So I said I like this, and this is kind of a more fundamental thing, and this is like a more it's more efficient way to find the model you can take, because the SPSS results not only one model but several of them. So let's see this, what I mean. So I click stepwise here. It did. All right. It's so quick. Okay. So descriptive statistics and this correlation coefficients, and between sweetness and lightness, sweetness chroma, sweetness A and sweetness B, except chroma, the other three attributes have a certain relationship with the sweetness. So it's desired, right? Okay. Then our concern is the multicollinearity, whether there is a correlation, large correlation among independent variables. So between lightness and chroma, well, it's quite small. Between lightness and A and B, so I think within this triangle, we can check out the pairwise comparison of 4 independent variables. And here I found that between chroma and B value, there is relatively large size of a correlation. I think this has been occurred because of our collection of a color chip, because our colors were they had a tendency toward yellowish and bluish. So it was my problem when I was planning the experiment. So which means if I have correctly collected the color stimuli, then actually the chroma and B shouldn't have such a large coefficient. And anyway, it's not small value, but it's not very high to be excluded from the multiple regression analysis. So let's take them all. And here it's the result of the stepwise method. So the SPSS proposes us 2 models, so we can choose one of them. The first model includes only lightness. So the first model has here as independent variable only the lightness and a constant. So this model pursues the simplest regression model, and this means that sweetness needs only the lightness information of a color to estimate the sweetness. But here the R-square value is 0.53. But if we include the A value, which means reddish or greenish, then suddenly the R-square value is increased up to 74%. So I think it's a quite high increase. So although the model becomes a bit more complex, we better take the A as independent variable. So as a result, I think in this case we better take the model 2, and this model 2 is providing an equation like sweetness equals to 0.020 multiplied by lightness plus 0.012 multiplied by A value plus the constant. That's the equation we can get. And then what is this standardized coefficient? That's relative size of the impact, because the lightness varies between 0 and 100, whereas the A varies between -100 and plus 100. And in multiple regression analysis, the independent variables can have been measured in different scales. So just by comparing the beta coefficient, we cannot really estimate which independent variable has a larger impact. So therefore, we should check the standardized coefficient column, and here you can compare the size of impact. And here you see that the lightness has a much larger impact than the A has.